Okay, the recording is on, so please start. Thanks.
Hello, everyone. Thanks for having me for this nice initiative called the Dual Mystery Channel of Gauge and Gravity, based in IIT Madras, Chennai. So, as you might have seen, I'm gonna talk about fragmentation equation, stochastic fractal, and Noether's theorem. If you are coming from a high energy background, which you most likely are, you might not know what the first two things mean, but I'm going to explain. I myself am a high energy physicist, so for me it's also some interdisciplinary work. And for you guys, if you are working in high energy, for you the things that you know, that things that you can connect will come towards the very end in terms of Noether's theorem. Okay, so the references for those of you who are non expert in statistical mechanics, there is a nice book by the father of fractals, Mandelbrot. His book's name is The Fractal Geometry of Nature. And then we're going to talk about fragmentation equation, and that has been discussed well in the work of Ziff and McGrady in 1985. And then we'll also talk about something called stochastic fractal, and that idea was introduced by Hassan and Rogers back in 1995. Hassan is my collaborator and colleague back in Dhaka. And then all these things, you can see a nice summary of it by a book recently published by Banerjee et al. The book was published by Francis and Taylor, named Fractal Patterns in Nonlinear Dynamics and Applications. And then finally, as you see, that we will talk about stochastic processes, and then finally we'll connect it to via Noether's theorem to quantum mechanics. And this connection has been discussed a bit in the work of Robert Graham, done in 1986. Here is a list of my collaborators. As you see, Professor Hassan is based in Dhaka University, and then you have Professor Wattis based in Nottingham, and then we have two grad students from Dhaka University, Noreen and Shanur Rahman. Okay. So outline of the talk. First, I will try to motivate you why these kind of studies are interesting, at least for a high energy physicist. And then I will give you a crash course on fractals, since you might not know much about it. And then I will talk about fragmentation equation, and I will explore the fractal nature of this sort of fragmentation equation, the system that is described by such an equation. And then I will briefly talk about a version of the Noether's theorem. I plan to talk a lot on this last thing, but I did not get much time to write a lot since it comes last, but I will try to explain this well, although I don't have a lot of slides, but I hope that I can manage. Okay, so motivation. So you might know that fractals appear in nature and in many different man-made systems, and they appear in seemingly disparate systems. They appear in physics, material science, computer graphics, botany, physiology, medical science, geography, laser optics, and whatnot. It's a thing that shows up almost everywhere. But we know that fractals in nature, they evolve in time, right? Like a cauliflower grows with time and through some sort of random process. The thing is that the fractals that you read in books, first textbooks, the mathematical fractals, they are not natural. Those sort of fractals, you just have them, God given. But what we mean by stochastic fractal is that something that grows with time, and after a long time you have such a fractal. So for stochastic fractals, you have like in fractal self-similarity, that I will tell you what it means, but you also have conserved quantities, and that's something crucial. And we know that conserved quantities are related to symmetry via Noether's theorem. We'll see that for a stochastic fractal we have conserved quantities, and then the question is there is also this symmetry of self-similarity, right? It's some kind of symmetry, and that's also a continuous global symmetry. And then you might ask, okay, are these things connected through Noether's theorem? And okay, and then this connection works precisely because there is an intimate relation between stochastic processes and Euclidean quantum mechanics. This thing has been known for a long time, and I think this was the thing that inspired Max Born to give the probabilistic interpretation of the wave function, for which he got the Nobel Prize in 1953, I suppose, or 50 probably. Okay, so before I move on to the crash course on fractals, do you have any questions so far? Professor Hassan, you might want to switch off your video. Okay, now let's see. So a crash course on fractal. What is a fractal as opposed to an Euclidean object? You might have a real line, or R2 or R3. These are all Euclidean objects, whereas fractal, as we know, is not a Euclidean object. But what it is? Let's have a look at this fractal cauliflower. These things we really see in nature, right? It's called the Roman cauliflower, and you see that both these things, this Euclidean object on the left and the cauliflower on the right, both are self-similar. Namely, you take a small part of it, blow it up, and it looks exactly the same as the big part from which you took it off. But there is a crucial difference, that for Euclidean objects, the density is uniform, whereas for for fractals, it has a non-uniform density. Namely, it has some vacuum or holes, and then some chunk of objects, so on and so forth, right? So this is so if fractal has some similarity with a Euclidean object and some dissimilarity, but there are more similarities as well. Say you want to subdivide this Euclidean object on the left side with boxes of size delta. Okay, so let's take box of size delta and see how many boxes will fit in this Euclidean object. So if the number of boxes that you need to fill up this Euclidean object is n, then you know that n goes like inverse to the power of the box size, where this power is the Euclidean dimension. In this case, it is 3. Okay, whereas for a fractal, this has exactly the same kind of Euclidean like power law. The number of boxes that you need to fill this object goes like some inverse power of the box size, but this inverse power is less than the embedding Euclidean dimension. So if, say, we call it d sub f, or fractal dimension. So if you take this cauliflower and try to find its fractal dimension, you will see that that will be less than 3. But sure enough, in the ideal case, you will see that this has a power law like this. Okay, so now let's move on to a textbook example of this fractal. So it's called a Triadic Cantor Set. So let's take an initiator of size 1, a unit interval, and let's divide it into three parts, and let's take away the part in the middle, and we do the same again and again. So at step 0, we have an initiator of size 1, and then at step 1, you have one interval removed, and the size of each removed or not removed is 1/3. Then at steps 2, you have removed two intervals, but the sizes of the intervals now go down to 1/9 or 1/3 squared. And at step n, you have 2 to the n-1 intervals removed, and each of size 1/3 to the n. So in this way, we go on and on. And in this way, after infinitely many steps, you see that you have removed all the length. If you sum up the length that you remove, it gives you 1. So you have removed all the length, but the funny thing is that still you are left with a non-empty set. To see this, let's compute the kth moment of the system after step n, and the definition of this after step n, or at step n, you take the kth power of each segment and sum them up. That gives you the kth moment, and this turns out to be this. Okay. So now you see that you can set the value of k to be ln 2 by ln 3. Then this value of k, you call it d sub f, or the fractal dimension. The value is less than 1, of course, and 1 is the embedding Euclidean dimension. And you realize that even when n tends to infinity, this df moment is conserved, is a constant 1, right? So in this case as well, we have a Euclidean object like power law, non-integer, because after at step n, you have each segment of size 1/3 to the n, and you are left with 2 to the n segments. So the number of segments is this, and the segment size is delta. So, and you realize that you have this power law formula where d sub f is precisely ln 2 by ln 3. So this is a fractal. Okay. Now there are more examples of fractals. In fact, many. I wanted to show you one which is called the Koch curve, and that's a model for snowflake, and it is an example of a continuous curve that is nowhere differentiable. This curve is fractal as well, and the fractal dimension is ln 4 by ln 3, which is less than the embedding Euclidean space, which is a plane of dimension 2. Okay.
Rakib,
Example 3. Yes.
Can I ask something?
Yes.
So in the Cantor set example that you were discussing, suppose the length that is being removed, okay, in the middle, that need not be say exactly 1/3, but say it's 1/3, or like instead of 1/3, it can have some kind of non-uniform mean, and with some fluctuations. Maybe it's a stochastic variable or something like that. So instead of say 1/3, it could be it could vary, and it can also.
Yeah, I think you are talking towards what I am going to say.
Okay, I
All
see. I see.
all these all these fractals are deterministic fractals because everything is fixed here. The rules are fixed, right? There
Okay.
is there is no notion of randomness, right?
Yeah.
So we'll see that once we have randomness, the things will change. Yeah. So
Oh, thanks. Thanks a lot. Okay. Okay.
that we'll see soon. Okay. Now, example 3, which will be relevant for the rest of the talk, is the dyadic Cantor set. Now think that we do the same problem, but now we split in two halves, and we remove one of them. Then for sure this will not not be a fractal anymore, because in the end you will be left with an empty set. But for the dyadic case, you can still make it a fractal if you say that after splitting it, you are gonna remove one of the daughters, say the one to the right, with a probability 1 minus p. Say if the probability is 75%, so it means that 25% times you throw it away. One out of 4, you throw it away. You may choose to throw it away or not, but with a certain probability, right? So with this, you see the different step. At step 0, we have an initiator of size 1. At step 1, we have a binary equal splitting and 1 plus p segments left of size half, right? Why 1 plus p segment? Because one of the segments will be there for sure, and the second segment will be there with a chance p. So the number of segments is 1 plus p. Likewise, at step 2, the number of segments is 1 plus p whole squared, and each has a size 1 over 4. And at step n, you have 1 plus p to the n many segments, each of size 1 by 2 to the n. And you see with the same kind of exercise is that the number of segments, asymptotically, number of segments and size of segment, if you compare them, you find a fractal dimension which is less than 1, right? And the fractal dimension is ln 1 plus p by ln 2. Okay. Now comes the question that Ayan just asked: what if we invoke some randomness? In this case, it will be called a stochastic dyadic Cantor set. So at each step we divide at most, and that's crucial, that we divide at most one segment, not each one of them. Okay, we divide at most one of them into two segments and remove one daughter segment with the probability 1 minus p. So at each step you have a randomness in choosing which one of the segments you will split, right? That's one kind of randomness that you have. And then there is another randomness, that where a given segment will you split. It has some length, right? So where in the length of the given segment will you split it, if you are not going to split it into equal halves. Okay, so with this kind of randomness and stochasticity, we also invoke the notion of time, because now at each point of time you have randomness. So now in this way, after a long time, you develop what we call a stochastic fractal. And for stochastic fractals, as opposed to deterministic fractals that I talked earlier, the self-similarity manifests itself through what is called dynamical scaling. And in high energy community, we know what this thing means, and that's where I try to connect to this work. So as I already mentioned you, we have randomness about how do we pick the one segment that we are going to split at a given time, or how do we split a given segment into two, right? These questions are captured by a quantity that is called the fragmentation kernel big F. Okay, so the fragmentation kernel incorporates the answer to this, the randomness that we are going to introduce. So with that, I go on to what is called the fragmentation equation. Therein, it's actually a continuous version of stochastic dyadic Cantor set, and fragmentation equation in this case particularly it's a binary fragmentation equation. You have some parts that splits into two. It's a stochastic process, because you don't know which part will split and where you don't know this. And so this kind of fragmentation equations, of course, as you might know, are used in polymer physics, in polymer chemistry to study polymer degradation. Okay, now here is the left hand side of our equation where you have the c. The c is a function of time and x, and the meaning of c is that c dx gives you the number of segments that you have at a given time t in the interval x and x plus dx. Okay, so it's segment density, if you like. So the left hand side gives you the rate of change of segment density, where the right hand side says you how it can go up or how it can go down. So it can go down by a loss term, namely a segment of size x can split, so you will lose them, or a segment of size y bigger than x might split into a segment of size x, right? So in this way you have this gain term. So I'm going to tell you what this f means, but roughly this gain term, you know now what it means. And we have this factor 1 plus p, because after two parts are split to give you a segment of size x, one of them might be thrown away, right? That's why we have this factor 1 plus p. If you don't throw it away, the factor would be 2 instead of 1 plus p. So now this fxy, that's called the intrinsic fragmentation kernel, that gives you the intrinsic rate at which a segment of size x plus y breaks into two different segments of size x and y. Okay, so that is inherent of the problem, and on physical grounds we can imagine that fxy should be fyx, because it does not really matter which one you call the right, which one you call the left part, it should be the same. And also it should not depend on how big is your yardstick, like how big is your scale. So if you rescale x and y, you are not going to get a different function, right? So you will get something that goes like the same function up to a factor. And we know in a high energy community these are called well, I mean, this thing delta is called the scaling dimension. So with this system, we have a stochastic process, and we also have a stochastic fractal if p is less than 1. Okay, if p is 1, this is still a stochastic process, but we do not have a fractal. We'll have a Euclidean space. Okay. So now what happens here? So this system, you might try to solve this fragmentation equation, and you realize that for long time, for time going to infinity, there appears solutions that behave in this way. Say time goes to infinity and particle size goes to 0, such that x to the delta plus 1 times t is fixed, where delta is the scaling dimension of the fragmentation kernel. And this kind of scaling solution exists for delta larger than -1. When delta is less than -1, you don't have the scaling solution, and some phenomenon takes place called shattering, and that in literature it's said that it's reminiscent of the Bose-Einstein condensation, because you produce infinitely many particles of size 0. Okay, so also in this case we have something called anisotropic scaling, and we know this very well in high energy physics. But the difference is that in high energy physics we usually talk about positive dynamical exponents z. In this case, as you see, dynamical scaling t scales as something which is different from x, and there is a factor z. When z is 1, there is the normal conformal case. When z is 2, we call it the Schrodinger case, and in this case z is negative, and unfortunately this has not been explored in the context of high energy physics. I have talked with some friend, some of you might know Arjun Bakchi, and it seems to me this kind of things might be related to Carolian physics, where the limit is that the speed of light goes to 0. Okay, so that's some comment for high energy people. But as you know that this dynamical scaling symmetry is there, and this will manifest itself in the fractal case in something, as we'll see, we call it data collapse, and you will see what it means. And this data collapse is precisely the signature of self-similarity in stochastic processes. Also, for this problem, there appears conserved quantity, namely that some moment, say n or df, some df's moment given by this is conserved in time, and this will be a function of course, the p that you have here, p, and your delta, thus the scaling dimension of the fragmentation kernel. So there is this conserved quantity. There is also self-similarity or dynamical scaling. Question to you is that, are these two things related via Noether's theorem? Okay. Any questions so far or not?
Sir, I am Shiraj from Dhaka, Bangladesh.
Yes.
Sir, can you explain anisotropic scaling symmetry? I am a bit confused about the term anisotropic. Why it is called anisotropic?
Well, that is some jargon in high energy physics. I don't know if the same thing is used in condensed matter, but the point is very simple. The value of z is not 1, so time and space, they don't transform the same way. That's it.
Thank you, sir.
Okay. So now we see how can we explore a bit of what I just said, right? Let's explore a bit. So for this, we need to choose a particular model, namely we need to give this f, right? Right now, all I have told you is that f should be symmetric and it should follow some sort of scaling. That's all. But now you need to choose.
Sorry, I have a question.
Yes.
So how do you and why is this scaling dimension I mean, why is this coming lambda to the delta factor when you
Here?
scale? Yes.
So
What are
this,
the physical arguments?
This comes just from physical arguments, right? You want to see if a big segment is more likely to break or a small segment is more likely to break, and then it does not really matter what is your units. Is this millimeter or centimeter or
Okay,
what?
okay.
Right?
Okay.
It's just
Yeah,
that.
yeah. Okay, thanks. So, but this will only work for delta greater than 0 or delta greater than 1 rather.
Well, I said for delta greater than -1, you have scaling solution, namely after a long time you will have this sort of behavior that t goes to infinity, x goes to 0, such that is true. That's called the scaling behavior. And throughout the rest of the talk, I will only consider the case where delta is larger than -1. Yes.
Okay, thanks.
Okay. So now we choose this kernel called the generalized product kernel. So what is it? Say you have the argument here y and x minus y. It means that you take a segment of length x and break it into two parts, one of length y, another of length x minus y. Okay, and this goes like x to the delta. So the fragmentation rate goes like x to the delta. But then this factor here is a symmetric beta distribution that gives you the ratio of y by x by a random distribution, right? That tells you where you break the segment of length x. That follows a beta distribution. Okay, symmetric one, of course, right? Because when we flip y and x minus y, you should get back the same thing. Now you can take this fragmentation equation and integrate it to find the rate of change of some given moment. Okay, when you do it, assuming that you have scaling solution, that after long time things behave in this way, with this assumption you can show analytically that the fractal dimension will be given by this transcendental equation. So you can solve for it for any given p and any given delta to find the value of fractal dimension. Okay, but the existence of a fractal dimension does not suffice for something to be a fractal, right? Because on top of it, you also need to prove that the system is self-similar. Namely, in this case, you need to show the existence of dynamical scaling. And throughout the rest of this part, I will prove this dynamical scaling via numerical simulation. So let's go to that. We used the Python programming language for this. Two of us used Python and a third one used probably C++, and we independently checked our results. So to do the numerical simulations, let's choose the initial condition that at the beginning we have a segment of length 1, right? So we have a delta function, and after a long time you expect the number of particles. So here there is a catch. Since it's a random process, we should talk about statistical things, right? So this n here is actually an ensemble average that I will explain you soon, and this delta as well. But roughly speaking, this log n and log delta should should have a slope of minus df, and here I plot log n versus minus log of delta, and this slope should be df. And we see that we have done it for delta equal to 0 and delta equal to 1 for the given value of p, which is 0.75, and we did this simulation for time step 1000 up to 100,000. Okay, and the number of such simulations was 10 to the 5, which means 100,000. So for different simulation at each given time that we plot here, these dots are dot at a given time, right, in the range that I mentioned. So at a given time, you take the ensemble average of the particle size, that gives you the delta, and at a given time you take the ensemble average of the number of particles, that is n, and then you plot it. So the
Okay.
yes.
So here delta is the size of the segment, or what exactly it is?
Delta is here, if you go
in the plot,
yeah, I will tell you, but first I think we need to know this. Here when I wrote it, delta was the box size, right? Now when you do this, these things you need to understand as a statistical average. So I have 100,000 ensembles. Okay, so I see each of them at a given time, say 1,000 second or 100,000 second. At each given time, I look in all of the elements in the ensemble, and I take the average of the size of segments, right, over the ensemble. Okay, does that answer your question or not?
Yeah, okay. So delta is averaged.
Yes.
Average on some.
Okay. Now from this plot, numerically you find that the fractal dimension is 0.700, and from an analytical consideration we know that it should be the same as p, okay, which is 0.75. So this matched, and the same thing happened when we take the value of delta, the big delta, which is the scaling dimension of the fragmentation kernel. Big delta is 1. In this case we get fractal dimension 0.7694, and from an analytic consideration it should be 0.66791, so on and so forth. We did these things for many different values of delta, and all of them matched. Okay, so this shows that we have Euclidean like power law behavior, but of course the power is less than 1, and it is a function of p and also a function of delta. The big, yes.
So here what you are doing, you are fixing n and looking at the average, the delta over the ensemble, right?
What is n?
So
what is n?
N is a number, or
no, I fix I fix the time. So you tell me the time. I fix the time, say 10,000 second. Okay. At that time, I have 100,000 different realizations, right? Each realization is a part of the ensemble, right? So I have 100,000 different realization at a given time, and in all these things I make an average over the particle size and also over the number of particles.
Ah, so it is an average distribution, an averaged
Yes.
curve. Ah, I see.
When you have a random process, this is the only thing that makes sense. Okay.
Okay. Thanks. Okay.
Okay. Now we are coming to the more fun part, which is the data collapse. So here we plot segment density as a function of minus log of x. I take this minus log of x to make this plot look nice. So as you see that minus log of x means what? As time grows, the particles become smaller and smaller, and the minus log of x grows. As you see that the blue curve is for 10,000 second, say 10,000 step. The yellow one is for 20,000 step, and the green one is for 30,000 step. So you have different plots, right? So in which sense these plots are the same? That's the thing. And this plot, as I see, is for delta equal to 1. And I mentioned the time. I think I said 10,000 steps, right? The blue one is for 10,000, and the green one is for 30,000. And in this case also you make an ensemble average on size 100,000. Okay, now comes the fun part, because now you can do something to see this, that all these plots are collapsing onto each other. So what do? We do in x axis, instead of plotting log of x, I think I made a mistake here. It should not be it should not be x squared t, but the root of that. So there is a factor half in front in the x axis. So I am plotting minus log x root t. So that is the combination that is fixed in the large t limit. So and then in y axis I have the probability distribution of segments. As you see, they are the same. It does not depend on time. Okay, so that's a sign of data collapse. Any question?
Sir, what is the dimensionless quantity on the y-axis?
That is the probability distribution of segments, right? So say you take this thing, right? X root t. So root t, you know, say take a given time, and then you know what this thing means. There will be a corresponding x, right? So
Yes.
you take a small range, and in that small range find the value in the y-axis on the curve. That will give you the probability, right? So if you multiply that value with the range, right, with the small range.
Okay.
So this is just a probability distribution function that gives you a value of 1. Okay, so I break the lengths into different length intervals, right, rescaled by time. such that I have this probability distribution, namely how likely is it for me to get some segment, right? So as we see that corresponding to the value of 2 point something, I have the maximum probability of finding a segment, right? But these things are of course dressed by time, and you see at different time they're not the same. Even if you plot these things, if you don't have time in the x-axis, rescaling of time, these things will shift towards the axis a bit, right? But when you do the appropriate rescaling, all these things, all these curves will merge to one. Okay. Now we wanted to talk about the conserved quantity. This plot is for delta equal to 0. There is this df's moment that we compute numerically. As you see that the df's moment is constant in time for each realization. Okay, if you take different realization, for each realization it's a constant in time. But if you take an ensemble average of all these different values, I don't know why all these values are less than 1, but it should not be. Some values should be more than 1, some values should be less than 1, such that when you take an ensemble average of different constants, you get 1. Okay, but it shows that even for one single realization in the ensemble, the df's moment is constant in time after a long time, right? So that's the existence of a conserved quantity. So you realize that the df is not 1, right? So this thing is not the mass, but this thing is actually the mass for a fractal, because fractals have fractal dimensions. Now, as I said, since the time is also short and I did not have also time to write down a lot about the next thing, I'm gonna say everything in one slide. But if you have questions, please ask me, then I will explain. So now I am going to tell you that this existence of symmetry, dynamical scaling and conserved quantities, are they connected through Noether's theorem or not? To see this, we use the fact that stochastic processes can be mapped to Euclidean quantum mechanics. To see this, we make the following change of variables. Namely, we make times purely imaginary, send times to it, and x, as we know that x is the length of segments, and x we send to r, because r I want to do it because r is the radial variable, radial coordinate if you like, whose value cannot be less than 0. And then the c, the density function c, we can write as this, some wave function squared. Now you see that this psi does not need to be real. Okay, psi can be complex such that c is real and positive semi definite. If you make these changes, you can prove that the fragmentation equation can be derived from a Schrodinger equation. So you can write a Schrodinger equation with a wave function, and when you massage it to write down the continuity equation coming from it, you get the fragmentation equation. Okay, so the fragmentation equation is the continuity equation coming from the Schrodinger equation once you translate back this transformation. But this Schrodinger equation is a radial Schrodinger equation which has no kinetic terms. I'm saying it has no kinetic terms, and it has a non-local, non-Hermitian potential. That's kind of strange. So to have, as I said, that the stochastic processes can be mapped to quantum mechanics, and of course there exist processes in which you get the Schrodinger kinetic term, but those terms involve diffusion, like in Fokker-Planck equation. So we don't have a diffusion term in the fragmentation equation, right? So here this term on the left hand side becomes the IH cut d psi dt, okay, the left hand side, once you write down the Schrodinger equation. The first term becomes a local potential times wave function, and the second, it is the second term that becomes non-local, as you see that you need to integrate over y. So this gives you a not just non-local but also non-Hermitian potential. So when you make this translation, you have a very strange kind of Schrodinger problem which has no kinetic terms. Namely, you have an infinitely massive particle, right? So m tends to infinity, and you have a non-local, non-Hermitian potential. Now with this Schrodinger equation, of course, you can also write down the Schrodinger Lagrangian, and that's well known, right? This Schrodinger Lagrangian will also have a non-local potential term, but there is a recent theorem by Oriti et al., which was my who was my former colleague here, that showed that even for certain kind of the kind that we are considering here, for this kind of non-local potential, you will have conserved currents, no problem. So there should be Noether's theorem. Now this Schrodinger Lagrangian has two different global symmetry, right? One, as we all know, it has the global phase transformation symmetry, right? This is well known, which gives you the conservation of the wave function. And as you have seen that we make this thing that the wave function squared is actually c. So it turns out that the conservation of the df's moment is actually tantamount to the conservation of wave function. But since you have fractal dimension in the when you write down the conservation of the radial wave functions, right, in 2 dimensions, say we don't have the angular coordinate here, which is theta, but in two dimension, when you want to write down the conservation of the radial wave function in the integration measure, you have a factor r. In this case, since you have fractal dimension, the thing turns out to be r df, as you see here, x df. So this is the radial part that comes in the measure, and this thing is constant, and that is nothing but the conservation of wave function. So as I said, this conserved quantity has nothing to do with the existence of dynamical scaling. This has to do with the existence of phase transformation symmetry, but that is funny and strange because this symmetry does not exist when you have the fragmentation equation, right? for the fragmentation problem, everything is real and you don't have this complex phase transformation. It's only when you do the mapping to a quantum mechanical problem you find this symmetry. And since the conserved charge is constant in time, it does not really matter if you keep time real or imaginary, the conserved quantity will be conserved. So you find this conserved quantity in the Schrodinger case, you weak rotate back and you still have the conserved quantity. But it turns out that the dynamical scaling has a different conserved charge. Okay, and of course it's a symmetry and it's a continuous global symmetry. There will be conserved charge, and that conserved charge is actually not that interesting anyway. So that will be the integrated loss term. So take this term, the first term, make the integration, okay, and then multiply it by time t. So all it is saying that this first loss term should go like 1 over t. So this loss term goes like 1 over t after large time. So when you multiply it by t, it becomes a constant in time. So this is to me, this conserved quantity does not have a lot of physical meaning, but this is actually the conserved quantity that corresponds to dynamical scaling. Okay, I think I would like to stop here. I also did not have time to write down a summary, but I can always answer your questions, and thank you.
Thank you for the nice talk. So let us take questions now. Please unmute yourself and ask if you want. Okay, in that case, let me ask something, Rakib.
Okay.
So essentially, you don't have a unitary revolution in the quantum mechanics picture?
Potential, your Hamiltonian is non-unitary, right?
Non-Hermitian, you mean?
Yes, right.
And, okay, so so what you're saying that essentially mod psi square is not conserved, but x to the power something times mod psi square is conserved.
And
that is exactly what you're saying.
And I forgot to tell you that in non-linear optics, this phenomenon is well known. In non-linear optics, they create some system in the lab where you have the corresponding Schrodinger problem has a non-Hermitian potential, and in this case as well, they see fractal dimension. For example, the kinetic term that they want to write for such a system, in the kinetic term, instead of the Laplacian, you have a fractional power of the Laplacian, say, right? So this is one way of seeing also that when you have this kind of non-canonical terms, I mean, you have the wave function is not conserved, but you have to multiply it by something. Yes,
I see. Okay, and
so, I have a question, please.
Yes.
So fractal dimension, does it depend on the capital delta, the
Yes.
scaling dimension of the
Yes.
kernel? So
yes, it does.
If the capital delta increases, what happens?
Yes. Capital delta increases, then the fractal dimension goes up, right?
And is there any limit?
Yes, that you know, right? So
So it becomes the deterministic case when you split exactly in the middle.
That's right. But what was the value in that case?
Log 1 plus p by log 2.
Right. Yes. So yes, he is trying to say that when my delta becomes infinite, in this case, this problem is tantamount to the problem of this Dyadic Cantor Set. So in this case, you get back to this fractal dimension log 1 plus p by log 2. Yeah, that's right.
So can you explain, please, what is dynamic scaling?
Well, that is just a name, right? When your space and time, they don't scale the same way. But you have a symmetry, right? When the value of z is 1, you call it a scaling symmetry. If your system has a symmetry of this type, that you scale your clock and your yardstick the same way, and that's a symmetry. That's called ordinary scaling symmetry. But anisotropic scaling and dynamical scaling are the same thing when the value of z is not 1. Yeah.
Okay.
TRG is there or not, Ayan?
I don't think he's in the audience.
I see.
Okay, one more thing. Have you looked into also, there's similar equation in QCD, like for soft text physics, like Jim walk evolution, and which have very similar characteristics, because the fragmentation here involves like splitting of gluons in the rapidity, and there's a rapidity coordinate. There's an x is analogous to a rapidity coordinate.
I would like to have a look at them, but I fear that in those cases the value of z is also not negative, right? Do you remember?
No, I don't remember that exactly. I mean,
I think that the value of z there is also positive. So which does not fit with this kind of problem.
I see. Okay, so any more questions? And okay, if not, then yeah, let's thank Rakib for this wonderful talk. And
thank you very much. Thank you.
Good to have you here, and yeah, and hope to see you back again.
Yeah.
Okay, then.
See you.
Okay, bye.
Okay, bye.
Bye.
Have a nice day.